We'll get started now. My name is Parth, and I'm a software engineer here at Rise. And Shri, do you want to introduce yourself?
Yes. Hey guys, my name is Shri. I'm an AI engineer on the DevRel team here, with a main focus on like evals and eval best practices. So now, kind of for the main event, I'm gonna hand it off to Peter here to introduce himself and talk a little bit more about his paper. He's been exploring why small, efficient models can match and even in some cases surpass their larger counterparts in agent workflows. So, Peter, I will let you take it from here.
Thank you. Right, yes. So for a brief introduction, I'm Peter. I'm an AI research scientist at NVIDIA, and I broadly research AI systems, which, I mean, these days is strongly associated with agentic AI, but you can also find them beyond agentic AI. The paper that I would like to tell you a bit more about here is work coming from our research group, Deep Learning Efficiency Research Group at NVIDIA Research. It was a larger effort, plenty of authors contributed, so I might be speaking today, but the ideas that are being presented are not necessarily just my own. And also note the email address at the bottom. We welcome correspondence on the subject. So the paper is titled Small Language Models Are the Future of Agentic AI, and it is a position paper. So one thing to keep in mind, you might be used to papers in deep learning and machine learning where people are presenting new methods, they're presenting new benchmarks, or they're evaluating old methods on new benchmarks. This is not that kind of a paper. So here, what we were trying to do is to put together all the information we've gathered on the subject, leading up to the publication of the paper, and to also create a starting point for a discussion on the subject, because we feel that it's quite important. And we've had various business motivations and engineering motivations to start this discussion. The position itself stands on three pillars. The first pillar of the position is that small language models are sufficiently powerful to handle many of the errands that the agents ask language models to do. Second pillar is that they're inherently more operationally suitable than large language models for the use in agentic AI. And finally, the third pillar is that small language models are necessarily more economical for the vast majority of use cases within AI agents. Combining all of these three pillars of a position together, basically, we kind of came up with a summarization that small language models are the future of agentic AI. Now, it is important to talk a bit about the motivation for the position. So I would say it was twofold. On one hand, we had feedback from enterprises that are working on AI agents, either for their internal use or working on them and then selling them to outside customers. The biggest pressure, I would say, starting early this year, was on them to increase their margins. So quite a few of these customers already captured large parts of their target markets. And now what they're looking for is to deliver some value to the business itself. So to hopefully keep the quality the same or even better if possible, but to decrease the cost at which they're providing these solutions that they get paid for. Another motivation coming from the enterprises we've been talking to various engineering groups was that we noticed that the field of agentic AI has stabilized sufficiently for the emergence of some patterns. So we noticed that quite often people, when they build agents, they're using tried and tested, maybe not even realizing so, but they're using tried and tested patterns, tried and tested blocks, and they're combining them into an agent. And this gave us encouragement because we realized that, if we can optimize a particular block, we can optimize this block across many agents. So the cost saving would not just be felt by one developer, one customer, but it would be felt by a great many, everybody basically who is using this pattern. So that was the business motivation, I'd say, and it was coming from many conversations with our partners. There is also a hardware motivation for this effort. So if you think about language model inference, right now we're not, at least on the side of the market, we are not in a situation where there would be a race to the bottom in terms of the price per token that companies charge for their frontier models or for the latest models. However, it might come to it soon enough. And when that happens, specialized inference chips, such as you might have already seen published by Grok or by Cerebras, will lead, obviously, because they're specialized. And so, there's various shortcuts that they can take. They sacrifice generality and they gain efficiency in return. Now, when you think about the design of such a specialized chip, usually it's a lot of SRAM that is connected with a lot of math units, and everything is kind of on a board, and the chip is quite expensive. But because there is no talking to a big store general memory, the whole chip is a lot more efficient. And then what happens is that even if you build such a chip, or when you build such a chip for a large language model, it becomes quite a bit more efficient than when you would run it on a general purpose GPU. But if you build such a chip for a small language model, you get a lot more acceleration when compared to the acceleration that you felt for the large language model. And this is because of the fundamental constraint of the speed of light on the chip, where the distance traveled by the signal can only be traversed at the speed of light maximum. You can't go any faster. And so having a smaller model translates to crossing a much smaller distance on a chip, which translates into a lower latency and higher throughput, which if you're charging or if you're being charged per hour of use of the chip, translates directly into cheaper per token and cheaper per query inference. So again, the motivation was twofold, but both of these things were in our mind when we were thinking about what might come in the next few years when it comes to development of AI agents. Now, before we actually dive into the various arguments that we put forth for the position, it's kind of important to agree on some kind of a definition of a small language model. Now, it probably won't surprise you if I say that lots of people disagree on what the definition should be. So we kind of created a working definition. We do not claim this is the definition, but it's a working definition for our purposes. And that is that a small language model is a language model you could, in theory, deploy on a common consumer electronic device and performs inference with this model at a latency that will be sufficient to serve one user to their satisfaction. And then, large language model, that would just be the complement of the set. It would be all the models that are not small language models. Now, obviously, I mean, most of the agentic small language models would still run in the cloud, but this is a rule of thumb approximation because it gives you a kind of a rough link between the consumer's cost tolerance and the cost of the inference as you would optimize a model for it. Now, note that the arguments that I'm going to be presenting here actually do not depend on this definition almost at all, but it's important to kind of have a rough estimate in the mind. And so one thing that we said is that as of 2025, we would be quite comfortable talking about models, most models below 10 billion parameters to be small language models, considering them small language models. Now, another small thing to note before we go into the arguments is that when you think about an agent, or most people think about an agent, they think about a large language model that is making all the calls. So it's both deciding, what the plan for solving a problem is going to be, which tools are going to be called, what pieces of context they're going to be called on, and so on and so on. However, what we see quite a bit in enterprise AI is that, and especially where process has been long established and we're just replacing humans in the process with AI agents, is that there tends to be a code orchestration mechanism that follows the rigorous process, and the language models are used for various language errands when they need to the process needs to understand language, or where conversationality is required so that the user feels like they're interacting with a human. And so on the basis of these observations, we distinguish between model agency, which is pictured on the left. There would be agency where the language model is deciding what to do and when to do what on what pieces of context, and the code agency or code orchestration, where code decides what happens and language model is used in selected spaces to run certain errands, basically. Now, going on straight for the first argument, and I think this is the main argument that needed to be kind of said out loud at the time when we were publishing this paper, is that small language models are sufficiently powerful to take place of large language models in many spots within your AI agent graph, if you think about it as a graph. Here we give a few examples. I'm not going to go through these examples in detail. The important thing to note here is that you can have small language models between 2 billion parameters and 9 billion parameters that will, on a subset of general benchmarks, perform on par or better than large language models. And so basically the way people build these models is they start with general pre-training as they would pre-train a large language model. And then they focus on a few general capabilities they would expect the language model to do well on and optimize the post-training for that purpose. So what you end up with in the end are models that, okay, may not be good at both coding and common sense reasoning or solving mathematical Olympiad problems, but individually, these models might be either very good coders or very good language reasoners or very good mathematical reasoners or very good at trivia question answering. So then when you're developing your agent and you're starting to think about, okay, which small language model you can branch off to fine tune for your own purposes, you can choose one of these models based on their general characteristics and then fine tune to your specialized task. All right. The second argument, I think this is actually the most popular argument for small language models, is that small language models are more economical in agentic systems. So it is a generally known fact that if you take a, say, 7 billion small language model, and this was something that was made quite clear when Llama 2 and Llama 3 were published, if you take the smallest of llamas, which is usually around 7 billion models, except for the very small llamas, and compare it to the cost of the largest llama in the family, and you think about latency and you think that, okay, I'm paying a constant rate per GPU hour, so what is my cost per token then if I utilize the GPU to the maximum? You end up finding out that your inference on a small language model is somewhere between 10 and 30 times cheaper than the inference of the large language model. And this, of course, depends on how long your input context is, how long your output context is, how many concurrent users you're hoping to serve with one GPU at any given time, and also whether the model is a hybrid model, whether it's a Mamba-based model, or whether it's a transformer-based model. So it is difficult to go into specifics here, but, or I mean, if you go into the specifics, it becomes a lot more complicated and more detailed, but kind of a rough rule of thumb is that you can have that order of magnitude saving simply by switching in one spot from large language model to a small language model, assuming that you can utilize that GPU with your traffic to the maximum. Other arguments in the direction of economy are that small language models are a lot easier to fine tune. So usually you need just a few GPU hours. It's really cheap to fine tune a small language model, and you also need a lot less data. If you try to do the same with a large language model, you would usually have to mix in a bit of general data, not to lose some general capability, and general fine tuning would become quite a bit more expensive. So we're talking about GPU days. Of course, you can take various shortcuts, but again, this is a kind of a rule of thumb. It depends on the use case. Small language models, unlike large language models, also have the hope of being deployed on the edge. Now, when we talk about the edge, we don't think about very small sensors or cameras distributed everywhere. We think more about consumer-grade GPUs, automotive applications, aerospace applications. So there is quite a bit of support, especially if you think about what NVIDIA is doing with its consumer-grade GPUs, toward enabling AI PCs. So toward enabling your PC to run conversational agents, run various computer use agents if you have to use them or if you want to use them, experiment with them. And so small language models really can be deployed, whereas a large language model would be very difficult in general to put on a small language model, on a consumer-grade GPU and run it with the latency that would make you happy with it, that you could converse with it in real time. And finally, this is more of a theoretical take, and we link studies to that in the paper, but people have noticed that if you take a large language model and you look at which parameters are utilized, which neurons are actually being activated for any given query, you'll notice that quite a few of them are dormant for any given query. They might be activated for different queries, but for any given single query, they might be dormant. And when we compare this behavior to behavior of small language models, we don't see that trend, which kind of makes us think, or which makes the community believe that small language models are also much better, simply by their virtue of being smaller and a lot more compressed and condensed to utilize all of their parameters. And the final kind of argument class from the main thrust of the position is that small language models are more operationally suitable. So as we mentioned previously in the cost, there is a greater general flexibility because they're smaller. So, you can send them a lot easier. You can fine tune them easier. You can investigate them if you're into mechanistic interpretability. You can investigate them a lot easier. There is a democratization aspect. If their small language models are more accessible, then a lot more people can come in, contribute with their own specialized models or build their own models from scratch. And then it becomes a lot more easy. It becomes a lot easier to choose the right model for your application because the whole spectrum of models is a lot more diverse. It's a practical fact that agents often, especially enterprise agents with code orchestration, often expose only a very narrow language model functionality. So if you look into any single call within a code orchestrated agent, or generally code orchestrated agent, quite often the prompt has been fine-tuned and it's fixed, and it's only the payload that is changing. And there you're using a generalist to do this very small task, which is, may not be the best use of a generalist. Also, agentic interactions necessitate a close behavioral alignment. So quite often when you're in an agent, you need to talk between code and a language model. So code quite often expects firm structure without any syntactical mistakes. And in order to achieve that, you would often prefer to have the small language model understand only one output format, say XML or JSON, and understand it very well. It is kind of obvious if you look at any drawing, any illustration of an agent, that agentic systems are naturally heterogeneous. So there's usually a lot of pieces that come together for an agent to work. And any of these pieces could in principle be handled, if they're invoking a language model, by a different language model. And finally, and this is something I'm going to touch on in a later slide as well, is that agenting interactions are natural pathways for gathering data for future improvement, for fine-tuning of small language models. So if you think about one of these fixed errands where the prompt is fixed and only the payload is changing and only the responses are obviously changing, you can log all of this traffic. And you can use this traffic with appropriate anonymization and with appropriate security precautions to improve your models for that one particular task in the future. Now, what you might have seen now might feel like, okay, well, there's all of these amazing arguments in favor of small language models, so why are we using them? So why isn't everybody using them, actually? And here we note that there has been a large amount of investment already into centralized large language model inference infrastructure, which kind of creates a business momentum to proceed further in that direction. Also, people quite often use generalist benchmarks to train, design, and evaluate small language models, which is a bit of a problem, right? Because they're never going to do well on all of the benchmarks at once. And so people are often discouraged by the results if they think about all of the possible capabilities a small language model could have at the same time. And finally, there's a lack of popular awareness. So in San Francisco, you don't get street cred by training small language models. You get it by training the trillion parameter language models. So, not that many people boast about training small language models. So one final practical takeaway from this would be what we sketch in section 6 of the position paper. And this is not theoretical. We already have at NVIDIA, we already have software toolkits, various pieces that you need in order to do this and do it very easily, even without any background in deep learning. And that is the large language model to small language model agent conversion algorithm. It's not really an agent conversion algorithm. It's more like one agent invocation conversion algorithm. But basically, the process is very simple. You choose an invocation of a language model. Usually, it's not on the conversational interface, but somewhere inside the agent where it's really trying to understand a piece of text, for example. You collect the data securely, of course. Then you curate that data and filter that data to choose only the good examples, only the successful examples, and make sure there is absolutely no private information that you might be bringing into the fine-tuning process. Then you cluster the data. Usually you have quite a bit of imbalance on the various topics or types of queries that you might have collected all the data on. So it's good to cluster and then rebalance so that your fine-tuning is effective. Then you select the small language model, as we discussed at the very beginning, somewhere in the middle, which is aligned with the general capabilities that you expect. So it can be a coding small language model. It can be a language reasoning small language model. Then you perform the specialized SLM fine-tuning on the rebalanced data from the various task clusters. And finally, you evaluate and you think, okay, do I need to change something? Should I go back? And because the small language models are quite cheap to fine-tune, usually you can do this several times till you reach your desired level of perfection. Now, as I already said, at NVIDIA, we already have software toolkit for all of this. So Nemo Customizer is a very good tool that allows you to fine-tune models with just REST API calls. You don't really need to set up anything. It's very good in this regard because a software engineer can very easily fine-tune a small language model. Nemo Data Flywheels and Nemo Intake are products that help you with logging and saving, secure saving of all the usage data. And finally, Nemo Curator can help you with the clustering and selection of the data and anonymization of the data. So this was a quick run through the position paper. I'd like to remind you this is a position paper, so it should serve as a point to start a discussion rather than to something to argue over. But arguments are obviously welcome. And in that spirit, correspondence is welcome at agents@nvidia.com. Thank you.
Cool. Thanks, Peter. Thanks, Peter. I think we'll move on to addressing some of the questions that have been left by the audience in our chats. So I'm just going to start from top to bottom. Let's see. Okay. We'll start with Siddharth. Are there any examples of small language models, and how big are they supposed to be considered? Are they supposed to be considered to be small language models versus large language models? Like what's that barrier?
Yeah, we touched on that in
I
one
see.
of the slides. It's also mentioned in the paper. So we kind of put a rough guideline for 2025 to be around, below 10 billion parameters. And
Mm-hmm.
most examples, we go into detail, including references in the paper. So if you check out the archive paper, you can find links to all of these models. In the slide, you can see a few already, coming from mostly the larger companies. Salesforce one, I mean, it might appear to be an outlier, but it's actually very good at tool calling, which many people appreciate in agentic contexts.
Mm-hmm. Okay.
Awesome.
Well,
I can do that.
Okay, cool. Go ahead.
So the next question that we have is, when describing small language models, do you include the idea of on device, like on a phone only, tablet only, or computer only?
So the way this is the definition, the working definition is phrased, it might appear to be the case. And in fact, this is something that we were initially aiming for. That being said, it doesn't have to run on these devices only. The reason why you want to still think about a small language model as something you could run on a consumer device, such as a tablet, a computer with a GPU, is that we already know how much people are kind of willing to spend on a GPU or on a smartphone, and we know how willing they are to recharge their phone every 3 hours or one day. And this, by a very rough implication, translates into how much cost they're willing to tolerate, even when that small language model is hosted in the cloud. I know this is a very rough argument, and we're happy to engage on that through correspondence, but it's kind of like, this is how we came up with it, and it seems to be well grounded in the consumer tolerance for the cost of use AI.
Got it. Awesome. Let me see. I think the next question is, what would you do to correct for biases when you're using a small language model? So basically, most LLMs are trained to avoid our biases, right? And so this behavior is kept in downstream tasks. So essentially, what would you do to correct it in the small language models?
So I have two quick answers to that. The first one would be that when you're building a small language model, you have a lot more control over what data you feed it, especially in post-training. And as such, you can really choose properly sanitized, verified data to make sure that biases are minimized. They'll never be completely eliminated, but you can make sure that they're minimized. And the second answer would be that, we're trying to phrase this discussion as SLMs and LLMs within the agentic AI. And once you're in the field of agentic AI, you do not rely on the model to do absolutely everything. You allow for a system to be built around the model to mitigate some shortcomings of that model. So if you think about biases here, and if we just imagine for example, a medical assistant application which might be giving some medical advice and you really want it to be unbiased, then the standard process in the context of agentic AI would be to loop in a knowledge base, take a model that will rely on the knowledge base, so, use retrieval, perform retrieval augmented generation on data that has been carefully curated, not to have too many biases. And if you're really concerned, you can also add various points where LLM acts as a judge to reflect, or a SLM acts as a judge to reflect on whether the output contains biases or not. So again, in the context of agentic AI, we do not leave all of the responsibility about, say, biases or safety on the model itself. We allow for many other things to come into the system to help with making it more reliable and safer for everybody to use.
Cool. That's good. So another question is, do most of these small language models support tool calling, and can they be used with MCP?
Yes, so most of these language models do support tool calling, although not all of them are as good as all of the others. So, you want to dive into the benchmarks themselves. There is the Berkeley function calling benchmark. I think it's at V3 now, which seems to be universally understood as kind of an indicator of tool calling ability. There's also the Gaia benchmark, which kind of evaluates tool calling in combination with some assistant tasks. So you want to look at the benchmarks that might reflect your use cases and then look at how these models perform on these benchmarks. When it comes to MCP, so MCP is something you can bring into your application with just the software. So you can query the MCP server for available functions, and then you can bring these into the system prompt to make the model aware of everything that is there. You do not need to make special arrangements for MCP to work in the general case for a small language model. Of course, if a model, has been very much fine-tuned for some particular task, it will use its general tool calling ability. But as a rule of thumb, MCP is something you deal with on a software level, and the outcomes of these calls you bring into the context, and from that point on, it's standard tool calling.
That's good. That's good. And then next question is there, are there any, like, this is a position piece, but are there any experiments to prove or support the points that you've made?
Well, quite a few of the experiments have been run by the papers that we reference in the paper. So I would recommend if there's a particular claim that you're interested in, it is almost certainly accompanied by a reference. You can click on that reference, and the papers are usually quite thorough in their experimentation. If you're interested in any particular experiments or particular claims that you feel are not very well supported, send us an email. We're happy to dig deeper into that. We're aiming for, a reliable paper that will be a bit timeless, that will survive on archive for a few years. So we'd be happy to revisit the writing.
That's good. And another question is, when there are reasoning tasks, shouldn't one argue that large language models would be much better than small language models? And also for non-deterministic tasks, says the question is how do you decide between small language models and large language models in terms of delegating them for tasks?
So when you're building an agent, you're the person who decides which subtask or what is a responsibility of which component. You can decompose a complex task into subtasks with a large language model, and then you can deal with them individually with combination of large and small language models. So if you're thinking about how do you decide, well, you have your cost tolerance as an agent developer, or your consumers, your customers' cost tolerance, and you also know, you can read on the benchmarks and you can see the general capabilities. So that will help you decide. That being said, one thing that I would like to bring to attention in this context is also test time compute scaling. So in great many of reasoning tasks, we see a benefit to running, say, a small language model, but 16 times over, and then looking at a majority vote of the outputs of the multiple runs. And quite often that really helps with the extraction of the information from the distribution predictions of the small language model and in providing a more correct answer on average.
Gotcha. Okay.
So
And we have,
I'm
go
afraid
ahead.
I'm going to have to run in a few minutes. So let me just quickly run through some of these questions, just to slightly speed it up. So
Go for it.
Jamie is asking whether these are enterprise-only products or if it's pricing public. So most of the NVIDIA software is available, is open source and available for everybody to use. And that which is not open source is usually at least available as a container free to use for small businesses and individuals. So you can check the licenses, but unless you're a large corporate, vast majority of the projects will be for you. All right. Let me just answer a few more. Why do I have? Okay, perfect. Well, Igor is asking about permissiveness of licenses and whether I think it's kind of a democratization question. I haven't had a chance to study it in detail, but I would in general agree that small language model, permissive licenses make models more practical for organizations. All right, I'm afraid I'm gonna have to go because I have a sync here. If someone could take a screenshot of these questions, I'd be happy to kind of write up something that could be sent out later. Alternatively, if you're really interested in getting your question answered, please feel free to email agents@nvidia.com. We do read through our correspondence. It might take us a few days to respond, but we will respond.
Sounds good, Peter. I captured the last few questions, so I'll send them your way.
Sounds good. Sounds good.
Awesome. Well, thank you, Peter, for coming on and making this content so digestible. And yeah, I really appreciate it. And thank you guys for asking questions. These are some really good questions.
Thanks for having me. Bye.
Bye, Peter.